Yes, this is the continuation of the previous video where we have discussed some characterizations of constant functions. That is the conditions under which an analytic function reduces to a constant function. Here we discuss some more characterization of constant functions based on Lobel's theorem. Lobel's theorem says that a function which is analytic and bounded in the whole plane must reduce to a constant. Equivalently, a bounded entire function is constant, as entire functions are functions which are analytic in whole plane. In other words, a non-constant entire function is unbounded. One can find several alternative proofs of this Lobel's theorem in literature. An immediate proof follows from the Cauchy inequality. The Cauchy inequality says that if f is analytic in a region omega and if C is a circle about a of radius r contained in omega, then modulus of the nth derivative at a is less than equal to mn factorial over r raised to the power n. For n is equal to 1, we have modulus f dash a less than equal to m by r. Now note that fz is analytic in whole plane. Therefore, we can choose the circle R as large as we please. So taking here R approaches infinity. We have f dash a is equal to 0. Now since a is arbitrary point of the complex plane, therefore it follows that f dash z is equal to 0 for all z, and therefore fz is constant. Now, this Lobel's theorem has many interesting consequences. First is exercise 1. A function which is analytic and whose real part is bounded in the whole plane must reduce to a constant. The idea of the solution of this exercise is that when f is analytic, exponential f is also analytic. And when its real part is bounded, then exponential f is bounded. And then we apply Lobel's theorem to exponential f, and then from this we deduce that this f is constant. Now let f is equal to u plus iota v be analytic and let its real part be bounded in whole plane. Consider this function exponential f. First note that its modulus is mod gz. This equal mod exponential fz. This we can write exponential u plus iota v. This equal exponential u and then mod exponential iota v. Mod of exponential iota v is 1. Therefore, this equal exponential u. This is less than equal to exponential mod u. As exponential functions are increasing functions and mod u is greater than equal to u. Now let u be bounded in whole plane, then mod u is less than equal to u naught for some fixed positive real number u naught. Also exponential functions are increasing functions, therefore mod gz is less than equal to exponential mod u less than equal to exponential u naught. So gz is bounded in the whole plane. Also note we now show that g is also entire. If g and f are analytic functions in the same domain, then the composite function g of fx is also analytic in the same domain. Here f and exponential functions are entire functions, therefore exponential f is also entire. Also note that we can write exponential z as exponential u and in bracket cos v plus iota sine v. Therefore capital U, the real part of g, that is exponential f, is u, capital U is equal to exponential small u cos v, and imaginary part capital V is exponential u sine v. Now using chain rule of derivatives of real variables, we have curly capital U by curly x is minus exponential u sine v curly v by curly x plus exponential u cos v curly u by curly x. Now note that exponential functions are continuous function and trigonometric functions are also continuous function. Now this partial derivative curly v by curly x is continuous. Why? Because f is given to be analytic, so its real and imaginary part have continuous first order partial derivatives, and same is true here. So curly u by curly x, this capital curly u by curly x is continuous. Similarly, we can find other derivatives and see that they are also continuous. Also note that curly u by curly x is curly v by curly y, and curly u by curly y is minus curly v by curly x. So the first order partial derivatives of capital U and capital V are continuous and satisfy CR equations. It follows that G is analytic in the whole plane. So G, that is exponential, F is entire and also bounded. So apply Lobel's theorem, we find that G dash Z is equal to 0. That is f dash z exponential fz is equal to 0. This implies f dash z is equal to 0 for all z. Why? Because exponential functions are never 0. From this, it follows that fz is constant for all z in complex plane. Now, exercise 2. A function which is analytic and whose imaginary part is bounded in the whole plane must reduce to a constant. Now, let f is equal to u plus iota v, and suppose v is bounded. Then consider this function h is equal to iota f, which equal minus v plus iota u. Then its real part minus v is bounded. So it follows from exercise 1 that iota f is a constant function, and hence f is also constant function. Note that it is clear from the proof of exercise 1 that the theorem is true under the condition that real part of fz is bounded below. Why? Because and also bounded above. Because if this u is bounded above, then here we can use this less than equal to exponential u naught. So it follows that this theorem also holds true under the condition that real part of fz is bounded above. It also holds true if real part of fz is bounded below, because in this case the real part of minus f will be bounded above, and then minus f, and hence f will reduce to a constant. Now exercise 3. If f is entire and this small m is a fixed real number such that mod fz is strictly greater than m and strictly greater than 0 for all z in C, then f is constant. Now note that this condition mod fz strictly greater than m strictly greater than 0 implies that fz is never equal to 0. So derivative of the reciprocal of fz, that is 1 over fz, this exists for all z, and also note that 1 over f mod is then less than 1 over m, that is this is bounded. So by Lobel's theorem g, and hence then f must reduce to a constant. Now exercise 4, show that an entire function with a non-negative real part is constant. The same is true if it has a non-positive real part. Let f be an entire function, then exponential f is also entire if real part is non-negative, that is real part of f is greater than equal to 0, then mod exponential fz is equal to exponential real part of fz, which is greater than equal to exponential 0. Why? Because exponential functions are increasing functions. This greater than equal to 1. By exercise 3, if gz is greater than m greater than 0 for all z in C and g is entire, then g must be a constant function. Therefore, g is equal to exponential f is also constant. So, as we have proved in previous exercise, g dash z is equal to f dash z exponential fz is equal to 0 implies f dash z is equal to 0 for all z, as exponential functions are never 0. So, f is constant. Similarly, if real part of f is non-positive, then exponential fz mod is mod of exponential real part of fz. This is less than equal to exponential 0. Why? Because the exponential function of real variables are increasing function, and this then comes out this equal 1. So exponential f, and hence f is constant by Lobel's theorem. It also follows on applying this exercise for to the function iota f, that an entire function with a non-negative or non-positive imaginary part is also constant. Thus, a non-constant entire function cannot map the whole plane only to upper, lower, left, or right half plane. Now, exercise 4, fifth 5. A constant function is the only function which is analytic in the extended plane. If f is analytic in the extended plane, then f is also continuous when z is infinity. That is, limit z goes to infinity, fz exists and is finite, say small l. Then apply definition of continuity. By definition, for every epsilon greater than 0, we can find r greater than 0 such that this mod fz minus l is less than epsilon for all mod z this greater than r. Now note here that on using triangle inequality, this mod fz minus l is greater than equal to mod fz mod minus mod l. And from this, mod fz is less than equal to mod l plus epsilon for all mod z greater than r. So fz is bounded for mod z greater than r. Also note that a continuous real valued function on a compact set has maximum and minimum. So if f is continuous, then f is bounded in mod z less than equal to r. Thus, f is analytic and bounded in the whole plane, and hence by Lobel's theorem, f must reduce to a constant. Now it follows from the above exercises that an entire function cannot map the whole plane onto the unit disk, but there are functions which are continuous on the whole plane and maps the whole plane onto the unit disk. For example, consider this function fz is equal to z over under root 1 plus mod z square. This function maps the whole plane onto the is also 1 1, and therefore also has this inverse. Also from this definition of fz is equal to z over under root 1 plus mod z square, we can write real and imaginary part of fz. This x over under root 1 plus x square plus y square plus iota y over under root 1 plus x square plus y square. Then we can see that u and v are continuous function for all x and y, and hence f is continuous in the whole plane. Also, we calculate partial derivatives of this u and v and see that they do not satisfy the Cauchy-Riemann equation in whole plane. So this function is not an entire function, but is a continuous function which maps the whole plane onto the unit open disk. So what we have, if we have this z plane, then an entire function cannot map this whole plane onto the unit disk or half plane or straight line or an arc. In the next video, we will discuss some consequences of Lobel's theorem related to polynomial functions.